Last meeting, we discussed number 6 for shearing stress and bearing stress. So for today, let's just continue on to number 7. So number 7, a rectangular piece of wood, 50 millimeters by 100 millimeters in cross-section, is used as a compression block shown in the figure. Determine the actual force P that can be safely applied to the block if the compressive stress in wood is limited to 20 meganewton per meter squared and the shearing stress parallel to the grain is limited to 5 meganewton per meter squared. The grain makes an angle of 20 degrees to the horizontal as shown. So, to analyze, we're given compressive stress and shearing stress. From that, we have to figure out what is the maximum actual force P allowed to be applied on this block. Okay, so first let's write our given. We have area 50 by 100, so let's write that. A 50 by 100. We can solve for that already. That's just 5,000 millimeters squared. We were also given compressive stress, which is just normal stress. So symbol for that is sigma. So in wood, limited to 20 meganewton per meter squared. However, we already know meganewton per meter squared can also be written as MPa. And then we also have shearing stress parallel to the grain, 5 meganewton per meter squared. So I'll write that shearing stress P, or rather this symbol, okay? Again, this means parallel, this means perpendicular. So parallel to the grain, 5 meganewton per meter squared, or simply 5 MPa. And then the last part is grain makes an angle of 20 with the horizontal as shown. So these are your grains, which can be considered as your inclined area. And theta is the angle from the horizontal. So theta 20. Okay. So let's start. Now recall from our past lectures, the amount of stress given is usually also the same as the amount of equations that we need to work on. We're given two, compressive and shear. So let's work on both. Let's start with compressive. So compressive stress, again, that's just normal stress. And the equation for that is P over A. For compression, there's no problem. P would have the same value as your applied force P since they're both perpendicular to the cross-section of your wood. Okay, so I don't have to solve for P. Actually, that's what we're looking for. This is given 20 equals P all over A. Again, A for compressive stress is the perpendicular area to the force. So that is just simply this, the cross-sectional area. So 5,000. From this, please solve what's P. Correct. Mariah and John. Cabero, Guico. It's 100,000. And then unit. Newton, millimeter squared, so the resulting unit is Newton. That's not our final answer yet. That's just a possible answer. Because we have to check for shear stress. Now, that's not just regular shear stress. As you can see, it's mentioned that that's shear stress parallel to the grain. So we can just use V over A. That's V over inclined A. Now, luckily for us, we've already derived the equation for that, right? And that's shear stress parallel to the incline, V over 2A, P over 2A, sine 2 theta. Okay? That's 5. P is what we're looking for over twice. Capital A is still the cross-sectional area. So I can just copy that 5,000 sine 2 theta. Theta being the angle between the incline and horizontal, which is given as 20. So 2 times 20, I'll just write 40 degrees. From this, please solve what's P. Make sure your calculator is in degrees. Correct. John, Benedict, and Nicole. Beltran, Sangonil. Correct. 77,786.19. And then unit, again, that's Newton. Not final answer yet, that's just a possible answer. And then the final question is, what is the maximum allowable? Okay, everyone please answer. These are our choices. Is it the 100,000 or 77,000? 100 or 77? Everyone answer in the chat. Okay, very good. Everyone got it correct. The answer is the 77,001. 77, 786.19 Newton. Okay, very good. Once again, when we're looking for maximum force, maximum load, we're going to choose the minimum of the values. Okay, that's it for number one. Any questions for number one? Please answer in the chat. Okay, no questions. Great. Let's have the final problem for shearing stress and bearing stress. Number 8. For number 8, a 7/8 inch diameter bolt having a diameter at the root of the threads of 0.731 inch is used to fasten two timbers together as shown in the figure. So these are your two timbers. This is the head, this is the thread, and this part is the bolt. Okay, the knot is tightened to cause a tensile stress of 18 psi in the bolt. Compute the shearing stress in the head of the bolt and in the threads. Also, determine the outside diameter of the washers if their inside diameter is 9/8 of an inch and the bearing stress is limited to 8,000 psi. Let's focus on the first question first. Shearing stress and bearing stress. So we're not looking for load as the final answer, we're looking for stress. Stress is simply force over area. Area is easy to figure out, right? The problem here now is force. Where am I going to take the force? It's not given. You'll take that from this. As you can see, instead of applied force, we have an applied stress. Okay, so your knot is tightened, causing this kind of stress, tensile. From that, we will get our force needed for the shear stress. Okay, so let's write the given. 7/8 inch diameter bolt, I'll call that D sub B. 7/8 of an inch. And then we're also given threads 0.731 and then tensile stress 18 psi. So on the thread, I'll write that as D sub T for diameter of thread 0.731 inch, and then tensile stress, so that's sigma, right? Tensile is the same as axial stress. So sigma is 18 psi. And then finally, diameter of washer 9/8. So I'll call that DW. Inner diameter DI 9/8 of an inch. And then we're also given bearing stress 800. So I'll call that sigma B. That's a symbol for bearing stress. Okay, that's the given. Let's start again with part A, figuring out shearing stress on the head and thread. And I've already explained, we'll get that shearing stress not from the applied force, but from the applied stress. This one. Stress equals 18 psi That's tensile. So the equation there is P over A. Okay. So this is 18 KSI, and again, KSI is just 1,000 pounds equals P over A. Now, what is that P? Let's draw a free body diagram to explain. This is your bolt, okay, the head, and then you have your thread here, okay? Now, as mentioned, this is going through tensile stress. So this is what that looks like, okay? Hold on. So the only way for this, or if this is experiencing tensile stress, then it is appropriate to conclude that this is also experiencing tensile force. And remember, tensile force is just away from the object. So that's your F. Okay? And this tensile force also creates shear force over here. This is the head, and then there's also a bolt here, and this is the area experiencing shear stress as well. So therefore, okay, that F is also the normal load P that we need in this equation. Okay? Because again, tensile stress, tensile force perpendicular to the cross section of the object. Right? And then that tensile force is being resisted by your shear force between the bolt and the head and the thread. Okay, so in short, there's a reaction force V here. So therefore, V equals P. Okay, so we just have to look for P, which is this. And then all over area. Again, this is still normal stress, tensile stress. So can anybody give me the equation for area if we're just considering tensile stress on a bolt? Hey, very good, Chloe and Jan. Wiko makrohon. It's a circle. Okay, so bolt, if you look at the cross section, that's a circle, and that is the perpendicular area to your resulting load P. So that's pi over 4d squared, P over pi over 4d squared, and D, okay, depending on, okay, the D here is for your bolt itself. So that's 7/8. Okay, from this we solve what's P. Correct, Stephen and Christian, Denaga, Horta. Oops. Correct. It's 10.82. Okay. And then unit. This is KSI. This is inch. So 1,000 pounds per square inch, inch squared. The resulting unit is 1,000 pounds, which simplifies to just kips. Okay. All right. Now we have P. We can finally solve for shear stress. Let's start in the head. Shear stress in head, I'll call that tau sub H. And that's just V over A. V is the same as your applied or resulting load P. A. Okay, so to illustrate, this is your bolt, right? This is what you rotate to tighten this screw. Your head is over here, and then this is the thread. So if you try to draw that, this is the head of your bolt, or of your screw. This is the bolt, okay, one that's tightening everything. As you rotate that, this portion is what's undergoing shear stress. Okay? So therefore, what's the area for the shear area? Again, what's the equation for shear area if that is what's happening? Correct, Cyrus. Tenorio, right? Yep. Who else? Anyone else? Correct, Jan. We go. Pi dh or pi dt. Why? Because that's just simply the circumference of the or perimeter of your bolt times its thickness, right? So pi dt. Okay, and then P is just simply this 10.82. So please store that in your calculator. And then P over pi D, diameter of head. Okay, so let's specify that DH, diameter of head. Now here at the top, the diameter of the head is this, which is also equal to the diameter of the bolt. So we can just copy that, 7/8. Thickness given 1/2. Okay, please solve what's the answer. Correct. Maria Janelle. Espanol, Lafredo. Maybe Fredo. Espanol. 7.87. Or if you use the stored value, it's 7.88. Okay, so 7.88. And then unit, again, upon checking, that's kips inch. Therefore, the resulting stress is KSI. Now, if we converted this to pounds, if you multiply this by 1,000, the resulting stress is PSI. But we didn't, so that's still KSI. Okay, so that's for your head. Now let's move on to shear stress in the thread. This portion, this is the thread. So same thing, V over A. So although it's a different portion, it's still experiencing the same shear force due to this normal load P. So that's still P. And then area same. Okay, we will neglect the dips here. Okay, so we'll just consider it as a smooth surface as well, since it's negligible, which is pi dt, pi diameter of thread times thickness of thread. Okay, again, P is this, kips, so keep that in mind. Pi, diameter of threads, given 0.731. And then thickness of thread, given in the drawing, 5/8. From this, we solve what's shear stress. Correct, Marino and Steven. Sacro Porca. 7.54. Again, unit, KSI. As you can see, for a bolt, the head is experiencing more force or more stress than the threads. Right, so that's part A. Now let's move on to part B. Part B, determine outside diameter of the washers. If their inside diameter is that, bearing stress to that. Okay, washers, what's that? It's this portion. Yeah. Now let's draw that in 2D, or rather top view. Washer is gonna look like this. This is your bolt. Your washer is this. Okay, or sometimes it's inside that. So basically, this is a washer, and your bolt is directly on that. Okay. And then what the washer does is the same as your bearing plate. If this is your bolt, right? Okay. This is experiencing force, which will cause this block and this portion of your bolt to push against each other. And remember, whenever there are significant surfaces in contact, in this case, the area of the washer and your object, there's going to be bearing stress. So the stress present in washers are bearing stresses. Okay, that's why this is what we're given. And then the equation for that is simply PB over bearing area. Okay? Now, PB, what's that? It's the force causing the pressure between your surfaces. In our case, it's the same as this, right? This force also causes these two to push against each other. So that's simply P. Okay, great. Now what about bearing area? Bearing area, if you remember, is just the contact area. A washer is a disc, so the contact area is simply the area of this washer. Again, that's a disc. So recalling area of a disc, that's pi over 4 outer diameter squared minus inner diameter squared. Okay? Area of a disc. Alright, and then from that, let's write our value. Sigma B is limited to 800 psi. So 800 equals P. Now, psi. P is kips. There's an inconsistency in unit, so I have to convert. Usually, you follow the unit of the stress. So, convert this to pounds. That's just times 1,000 or times 10 raised to 3. Okay? And then all over pi over 4. DO is what we're looking for. And then minus inner diameter given 9/8. 9/8 squared. Okay, from this, please solve what's DO. Correct? Janelle and Maria. Dofredo Espanyol. 4.3 or 4.30. Unit, PSI, pounds per square inch. This is now pounds, inch, so diameter is in inches. And that's it for number 8. Do you have any questions? Please answer in the chat. No questions? Great. That ends our topic for shearing stress and bearing stress.